Okay, let's continue. So we were here. I think again we lost the connection. So let's continue. I think we have to draw a straight to be nothing complicated. I think should be in the middle. So as you can see, it is, but I think I have to change a little bit. I think we have to do 0.75, and then we can hopefully get it back. Yeah. So this is how we can do it, and then after we should delete all this. We can draw common potential concept here. So let's write, let's run it for R equivalent. Yeah, it's fine for right now. So RIP will be 5 kilo ohm. So let's move on to problem number 12, I guess. Let me indent this part first. So we have to indent, and let's begin the solution. Let the copilot suggest first, then we will modify. So this is a concentric oh yes, so this is, oh wow, this is right. So let the equivalent resistance between two sphere be AB. Yeah, absolutely right. Hence length is the wire and H is the area of cross section of the wire. As the sphere are concentric, length of wire will be P minus A. Now the question will be the area of the ring. Okay. I actually don't know how this is solving. I don't know really. Concentric, this is a sphere, man. How can you just subtract this part? You just don't know. No. Actually, it got accidentally right. It's not right. So let's remove everything, and then we can proceed with the differential equation. The resistance between two spheres will be. So firstly, as you can see, all the spheres are concentric thin set. So enter text. So we can assume that the concentric sphere that this spherical cell can be made using very thin spherical cells of thickness dr, and all these cells are like हर एक सेल किस तरीके से कनेक्टेड है. All these cells are interconnected. All these cells are interconnected in interconnected in series with each other. So let's into text. Let's find out. Let's find out. Let's assume a thin differential. Differential cell of thickness dr and radius r. So now we can find resistance of this sensor is dr. Yes, it's all right. Then dr will be dr 4 Pascal. Yes, absolutely fine. Now integrate this to find out total resistance. A to be dr. Let's run it, then after we can move on to second part. Yes, so as you can see, assume that this spherical cell can be made using very thin spherical cells of thickness dr, and all these cells are interconnected in series with each other. And let's assume a thin differential of thickness dr radius r, and let the resistance this will be dr. So dr is the thickness. Integrate. And that means it will find the summation. So yeah, it's absolutely right. Integration is just adding the differential resistance for every element, and that is why we can integrate, because integration is just addition, and these resistors are connected in series. That means we can simply add R1, R2, R3. So yeah, this is absolutely fine. And let's move on to problem number 13. I am taking too long, like 5-6 hours of live time to solve just one paper of 30 problem. No problem. Let me just finish this one and then see. So again, two satellites A and B have the masses m into m. A is in a circular orbit of radius r. B is in a circular orbit of radius 2 r around the Earth. The ratio of the kinetic energy to age. Ratio. So as you can see, it unfortunately got the wrong answer. Actually, it already given the mass. Let the mass of the Earth. Mass of the Earth is m. Is absolutely right. Let the velocity of age v velocity of v, right. As the velocity in a circular orbit, we can apply the equation of circular motion. Gm upon r square Vs is absolutely right, Va, and similarly it should be half sorry, mv square upon r is right. Gm upon 4r, their ratio of kinetic energy. So yes, half mv square is absolutely right. Then I think solution is right, but option is wrong. I don't know. TA ratio of the kinetic energy, or what's the problem here? Solution is right, but option is let me say it's from Gravitation, previous year problem, JEE Main 2019. So let me check it in the DC Panda series. Gravitation, yes, Gravitation, and 2019 escape velocity ratio. Where is ratio? There is no ratio. Motion of satellites, hopefully. Yes, this is one second. I think we got the problem part. So this will get cancelled out, right? No. 4 will turn to that. Yes, absolutely right. Let me check the solution to which topic. Which topic? Motion of slide, topic number 3, problem number 2. Topic 3, problem number 2. On D, absolutely right. Let me check the solution. So yes, velocity, everything is okay. 1 second, man. Oh, sorry. We put it the wrong mass here. How can you say the mass for the how can I say mass will be equal? No, mass will be unequal. And similarly before that also mass is not equal. So as you can see, simple mistake can be fatal here. So for B, mass will be 2 times m and 2r square 2 times m. Here absolutely fine. And then right now PV is equals to yes 2r. I have to 2r square 2r will get 2r will get cancelled out. Is it right? Let me run this, then we can verify that after. So as you can see, this 2m will get cancelled out, 2r will get cancelled out, and that means 2r. Yes, absolutely right. So velocity of V is right now. We can let's run this and check it out what it is substituting in the equation. Half m v square. So here it's wrong. Half m, not half into 2m into v square for the particle V. And now we can move on to second part. dA half m v square. No. Half into m 2 times v square. Yes. Yes, 2 times v square, and then we can put let me run, because we are now no causes at every step. Yes, 2 will get cancelled out everywhere, and ratio hopefully will be 1. Yes, so now it's right. So this is the final answer of the ratio d upon dp is equals to 1, which is the right answer. Let's move on to 14, and 14 is kind of interesting because it's from magnetism, and I don't think it can tackle magnetism still. Oh, it did, but now you can see at the end just messing thing up. So let me let's do from the beginning, and then we can. What is wrong with this part? Oh, right arrows, everything is right. Let's begin a line, and then we can add into text. Let me first this was let me read this first. A uniformly charged ring of radius I rotated about its axis with a constant linear speed v, and of each of its particles, the ratio of electric field to the magnetic field at point P on the axis of the ring at distance x equals to r. It seems horrible, but let me. Yes, we have to find the ratio. That means we have to firstly assume the amount of charge. So let me explain what will happen. As the ring is charged, as the ring is uniformly charged, and we assume the of a very thin ring of thickness. No, not thin, uniformly charged. Uniformly charged. And we can assume its its linear charge density to be lambda, and let this let me proceed. So firstly find out into text let me let's find out electric field first. Electric field find out it was no at point P oh come on Jet. What is happening? I think it's just it's not responding. So let me I don't know what is happening with this. So what to do? Electric field at point P. Delete. Let's run it first and see where something is wrong. I think no, nothing is wrong. As the ring is uniformly charged, we can assume its linear charge density to be lambda. Yes, absolutely right. Not up lambda. I think simply lambda will be okay, I guess, because up lambda is kind of attitude problem, and simply lambda is beautiful. Let the electric field to be it, and E will be like yes, absolutely fine. Let's I think I can use Q upon, let's say we have to, let's say Qx plus R square right per power 3/2. Let's run it first, then we can modify after. So yeah, Qx, and now Q will be 2 pi r. So now we can place no man, let's let complete this thing, diffraction. Yes, let's run it first. Lambda 2 pi r, so it seems intelligent. Lambda 2 pi r x, yes, then we can put r square here as well. So this is the electric field. Let's run it again and see what it got. 1/2, yes, 2 pi will get cancelled out, 2 will remain, 1/2 epsilon lambda rx is absolutely fine, and this will converge to 2r square. Sorry, 2r square. That means we can remove this part. It's quite complicated, man. I don't want to solve this. I think some other way must be easiest one. I'm solving in the much more complex. Or am I right? I don't know. RQ, yes. 2 pi power 3/2, it's absolutely fine. RQ. Let's R square. Yes, 2 epsilon lambda r, yes, absolutely fine. And now we can now VB and guess I think QB upon x square. No, magnetic field does not work like that, son. So we have to apply Bayes-Ford law, or you can say I cross tail. So if you remember this thing, you can directly apply, or you can just check it out. So I'm gonna check the expression for magnetic field, because I'm not going to drive here everything from the like scratch, that will be like tedious job. So for right now I'm gonna use the expression for the magnetic field. So where is the magnetic field? I like scrolling this mouse and that I don't just go to the content, I just love scrolling. So yeah, we are in the magnetism, and we are going to find the magnetic field due to a ring on its axis. Bayes-Ford law, yes, we are about to find out. Yes. So as you can see, no, this is not ring. This is at the center. Loop thing, yes. So yeah, as you can see, mu naught by 4 pi got cancelled out. I think we can drive it quite easily, but I'm not interested right now. So for right now we can use this part. Mu naught, this is mu naught, here it's alpha naught, but actually this is mu naught, and after integration I think it got like 4 pi got cancelled. So this is mu naught by 2 IRS square, yes, similar fashion. So let's use B is equals to d frac. So mu naught to up mu will be fine here, mu naught by 2, and then again we can use diffrac, and inside the diffrac IRS square. So as you can see, n is 1 here because this is a single ring, so IRS square, and then after IRS square z square p power 3 by 2. So current will be I, and then IRS square, and then we can use the left, and let's say x square plus r square power 3 by 2, and let's save it first and run this part, then after we can modify. So yeah, as you can see, it's totally fine, but one more thing I have to be careful about: how can I find the current in this equation, because charge is rotating with velocity v, and we're going to find I. So one idea I have in mind is I is basically rate of flowing charge. That means we can change, I don't know. So let's continue like this for right now. And oh, 1 second, we should not have found out all this crap thing. We could have like, oh, let's leave it like that, not R, just leave it like that. it will, I think, hopefully solve the problem, and leave it like this. Yes, it's absolutely fine. And then after we can speed, we can assume to be constant. So yes, current to be constant. Q into 2V. How it is getting Q into 2V in the business? I don't know. Q into V. Q into V will be I. No, that's not. So I got this. Q upon time period, that will be awesome. So let's find out the current. So current will be like Q upon 2pi. So let's say diffract. Or say, let's calculate. So current will be like then we can use application, yes, Q by T, and then it's equals to diffract. Q is lambda. Lambda times 2 pi r, and time will be 2 pi r, then again diffract. So this will be 2 pi r upon v. So let's run it first and then see what we can do. So as the rotating with constant linear speed, we can assume the current to be constant. So current will be like Q I T lambda into 2 pi r, 2 pi r upon v. So yeah, lambda times v. So let's, oh man, right arrow, lambda times v. Yes, it's absolutely fine. Now yes, it's no diffraction positive. sorry. We have to find out the ratio of electric field. That means electric field to the magnetic field is equals to, yes, let's run it first. What it is is equals to lambda v. Oh sorry, b means the line break. So let's run it again, and it all will get aligned. So yeah, it's all now aligned, and we put the electric field, which is qx, is absolutely fine. Again we put the current equation, absolutely fine. And now let's see what it suggests, and let's we can directly cancel out this part. I think that will be, let me remove this, scrap the last part, and let us start with diffract. Hopefully it suggests some, no, not suggesting anything. So as you can see, limitation of copilot thing. Copilot is not limited, but as you can see, it is quite limited in terms of intelligence, basic intelligence. So x square plus r square by power 3 by 2 will get cancelled out, and we will have like qx. So qx, and then after it will I don't know what to do. Yes, it will be like 2qx. Yes, 2qx, and downward part will get cancelled. So 4 pi will remain, epsilon naught will also remain, and then we will have no, let this part, let's remove this part also because it's also crap. So yeah, 4 pi epsilon will be here, and hopefully mu naught will be here. Mu naught is also here. 2 is a bird, and I square, yes, I r square. So let run it first, then see. Oh, where missed? Oh man, come on. Let's copy this part. And then let's delete command V. Yes, it's right. And then run visually. So yeah, as you can see, E by V is it will get cancelled out, and 2 will get in the numerator to qx upon 4 pi epsilon naught, then mu naught rs. Yes, I ask, and now we can, it's like let put some spaces, extra spaces, that will hopefully do the job. 3 millimeter will be fine. And now yes. So again we can use 3 millimeter distance gapping between the equation. So instead of q we can put lambda into 2 pi, lambda into 2 pi r, yes. And in terms of c dot, again instead of x we're gonna put, so yeah 2 pi seems right, lambda is right, v r square seems right. So now let's continue with the flow and see what happens. So as you can see, oh man, lambda got cancelled out. No, it's just messing thing up. We have to do like c dot. This is the problem of Copilot. Just it should do these kind of thing, basic stuff, not the complex stuff. But no, look, it will just substitute everything up, and it will get so. I do not want this. I want. Let me start from the previous line. Let me change this. So we will have like r square will get cancelled out, 4 pi will get it cancelled, lambda will get cancelled out, and that means in numerator will have only one, and 4 pi is get cancelled out, lambda will v, that means mu naught epsilon naught. So epsilon naught mu naught times v. Yes, it's right. And this is what I wanted. And then after we can put mu naught 1 by mu naught is like c. Yes, so 1 upon so this will be like 1 upon c square. Yes, so now we can directly say c square upon v square. So yeah, it was quite long, c square upon v square. It's a difficult question. Oh yeah, it was quite difficult, but not that difficult. If we will be solving from like fundamentals, just using the Bayes-Word law, then we may be facing some difficult challenges. But if you are using derived expression for the electric field and the magnetic field, it's okay. to be this complex. It's not always like lovey-dovey. We'll get simple equation for every time. And let me put 3 mm here as well. Oof. Yeah, it was difficult. I think one more easy way would be like you can find out the differential electric field as well as the differential magnetic field, and from there you can move forward, because both fields are yes, both are vector field. That means we have to find out the component, and hopefully component will get cancelled out of the electric field and magnetic field. That way we can solve easily. Yeah, that's possible if you don't want to use any expression. I think that will be better. Should I try that?
Sir, dinner? Huh?
Okay guys, see you around after dinner or something. For right now,